This is section 4.1b, radian and degree measure. So today we're going to continue talking about radians. We just introduced the concept in the last section. And radians, as you're going to see, they're a lot more convenient in some ways. And really, the measure radian is more logical than the measure degree, which is basically arbitrary. You know, there's no reason that there have to be 360 degrees in a circle, or it could be 400 or 500 or 1,000 or 200. But radians are not arbitrary. They're not based on human convention. Radians are based on logic. All right, so this is something we saw yesterday in the last lecture. We saw that arc length equals radius when theta equals 1 radian. That is the definition of 1 radian. The definition of 1 radian is the angle at which arc length equals radius. Okay, so that's nothing new. That's from yesterday. But the reason I'm putting this on the screen again now is because I want to introduce a couple of new formulas and see how we get them. So these are the new formulas. Theta equals S over R, and S equals R theta. So let's see why these are true. First of all, if we're looking at theta, in this case, theta is 1 radian, and S equals R. Well, obviously, S over R equals 1. And that's because anything over itself equals 1. You know, 3 over 3 equals 1, 4 over 4 equals 1, 6,000 over 6,000 equals 1. So if S equals R when the number of radians is 1, then it follows that S over R, which equals 1, equals the number of radians. And that's exactly where this identity comes from. Theta equals S over R. Theta, in other words, theta in radians, is the ratio of S to R. Now, what follows from that, of course, is that S equals R theta. And this formula, S equals R theta, is simply a consequence of the first, theta equals S over R, because you just multiply both sides of this equation, theta equals S over R, you multiply that both sides by R, and you get R theta equals S, which is the same as S equals R theta. All right, so these two formulas really are simply based on the definition of a radian. That's where they come from. Now, an important note, this is true only for radians. You can't use the S equals R theta or theta equals S over R formulas when you're dealing with degrees. And that's because something interesting, radians, even though they're often written with RAD, radians is a measure of angle that can stand by itself because technically radians have no units. Now, why is that true? Let's look at this ratio here. Theta equals S centimeters over R centimeters. It doesn't matter what S or R happen to be. You can plug in any number you want there. You know, you can plug in 6 for S and 2 for R. You'd have 6 centimeters over 2 centimeters. It's not important what the quantities S or R are, what the quantities S or R are. It doesn't matter what those quantities are. What does matter is that my numerator, S, has a certain unit, centimeters, because it's a length, and my radius, R, has a certain unit because it's a length, and that's centimeters. And notice that they cancel. You can cancel units just like you can cancel any other numbers when you're dealing with fractions. And since the units cancel with the ratio S over R, then technically theta in radians has no units. Theta in radians is simply the ratio of S to R. I'll say that again. Theta in radians is simply the ratio of S to R. And as you know, a ratio is just a number. It has no units. Okay, that being said, you will sometimes see radian angles written with RAD after the number. And a lot of times you'll see radian angles simply written as the ratio, like pi over 6, or 3 pi over 4, or 5 pi over 6. And that ratio will simply stand by itself because technically it has no units. It's just a ratio. Here, let's do this example. A small pizza is 12 inches in diameter. If I cut from the center to the crust, and then cut again from the center to the crust at an angle of 60 degrees to the first cut, how long will be the crust of the resulting slice? All right, so pause the video, do this on your own, and remember that your formulas only work for radians, so you may need to do a conversion here. So pause the video, and then when you have an answer to this question, resume. So this is the answer. S, the arc length, that is the length of the crust, equals 6, because 6 is my r. If my diameter is 12, then half of that is 6, so 6 is my r. And pi over 3 is my angle, my theta, because since the formula S equals r theta only works with for radians, I need to convert 60 degrees into radians, and that is pi over 3. We learned the conversion yesterday. And pretty soon you'll get to the point where you're able to do that conversion in your head, because pi over 3 and pi over 2 and pi over 6 and multiples thereof are common radian angles that you need to basically memorize before you get to calculus. But don't worry, that'll come naturally. So the answer is 6.28 inches, using the formula S equals r theta with theta in radians. Linear and angular velocity. Okay, now this is a concept that is simple for some and very difficult for others. So you need to pay extra attention, and don't be surprised if it's difficult for you. I've had students who are really good in math who sometimes just couldn't handle angular velocity. All right, so do your best, and don't worry. You can always replay the video or a certain portion of it. I'm also going to, on the next screen, have a physical model to demonstrate these concepts. But you know, even after all that, if you're still having problems, we can talk further about it in class. Velocity equals distance over time. All right, this is just a review. I'm talking about velocity as we're used to speaking of it, or speed if you like. It's just distance over time. You know, we talk about miles per hour when we're on the road, 65 miles per hour, 70 miles per hour. It's just, those are the units of velocity, distance over time. And miles per hour is just miles, which is a distance, over hours, which is a time. All right, so that's just to review the concept of velocity. That's nothing new. Now, let's also keep in mind that S, which we've been talking about, is an arc length. And anytime you're talking about length, you're talking about distance. 2 inches is a distance, just as 3 miles is a distance. All right, with those two concepts in mind, let's now get to the meat of this screen. On a rotating circle, the linear velocity v is arc length over time. It's still distance over time, but in this case, we're talking about arc length over time. And it's called linear velocity because it's the velocity at any point on the rotating circle in a tangential line. Okay, you could always have a line tangent to the edge of a circle, and at that particular point in time, it has a linear velocity denoted by arc length over time. And don't worry, we're gonna talk more about this. This is just to have the definition straight, and then in the next screen we'll see exactly what linear velocity and angular velocity are. Just make sure you record these accurately. And the main thing for now is to notice that since I have arc length over time, it's still just distance over time. That's all linear velocity is. It just happens to be on a rotating circle. V equals s over t. That's how I express linear velocity. V equals s for arc length over t for time. V equals r theta over t. And that equals r theta over t. Now, why? First, let's look at this. Why is it r theta over t? Because s equals r theta, and so I can just put r theta in for s. We've already demonstrated that. And so v equals r theta over t. And because you know, multiplication and division are associative, and I don't know if you remember that from Algebra 1, but you basically do them in order from left to right, so it doesn't matter, you know, where you put the parentheses when you just have a bunch of multiplications and divisions. Well, then r theta over t is the same as r times theta over t. You can prove that to yourself too with just random numbers. Try 2 for r and 3 for theta and 4 for t, and play with that, and you'll see that um, 2 times 3 over 4 is the same exact thing as 2 times 3 over 4. Anyway, let's get to the next step. On a rotating circle, the angular velocity, omega, it's not w, that's the Greek letter omega, is radians over time. Radians over time. How many radians the rotating circle goes through per unit of time? And omega equals theta over t by definition. Theta for radians, t for time. Omega equals theta over t. That's not a formula, that's just a definition, just as v equals s over t is not a formula, it's just a definition. And now we're going to put all this together into the most important formula for relating angular velocity to linear velocity, which is v equals r omega. V equals r omega. Now, where did this come from? Well, notice that what I'm circling now with the mouse arrow, theta over t, is the same exact thing as omega. And so this r theta over t is just r omega. And therefore, v equals r omega, because now what I'm circling shows that it relates to v, the linear velocity. V equals r omega. And this basically just says that the linear velocity depends on angular velocity. Now that's common sense, right? If a wheel is, let's say the wheels on your car, if the wheels on your car are going with a high angular velocity, that is, they're rotating very quickly, going through a lot of radians per unit of time, well then the linear velocity of the tire edge, which basically translates into the linear velocity of your car going straight, that linear velocity will be high. All right, and it depends on radius as well, because if you have a small wheel that's spinning quickly, it's not going to give you the same linear velocity as a large wheel that's rotating at the same speed. Okay, now all this should become a lot more clear in the next
demo of linear velocity and angular velocity. Now just keep in mind that the person in the demo uses the term tangential velocity. That's just a synonym for linear velocity. Tangential is the same as linear.
We're going to relate tangential and rotational velocity. We're going to begin with a simple demonstration. On the tire, there are two letter E's that are the exact same size, but one of the E's is located at a point near the axis of rotation, whereas the other point is located on the rim, a point that is farther away from the axis of rotation. What you should notice is that the E that is near the axis of rotation is easily recognizable as the letter E, but the E near the rim is blurred. In this video, we're going to talk about why that is. There are two ways to describe the motion of a rotating object. You can talk about the object's rotational velocity, which is how fast the object rotates through a given angle in a given period of time. Now we write that as omega, which is the object's rotational velocity, and that equals the change in the angle, usually expressed in units of radians, divided by the time it takes for that object to rotate through this angle. The other way we can describe the motion of a rotating object is to talk about the object's tangential velocity, which is the velocity of a point on the rotating object. And we write that as a v with a subscript t indicating it's the tangential velocity, and that's going to equal the distance that a point on that rotating object travels through divided by the time it takes for that rotating point to travel through that distance. Now in this video, we're going to talk about the object's rotational velocity, and we're going to talk about the object's tangential velocity, and then we're going to show the relationship between the two quantities. Now the first thing we're going to do is we're going to talk about the object's rotational velocity, which is often called the object's angular velocity, which is again how fast this object rotates through a given angle in a given period of time. Now we said that we can write the object's rotational velocity as the change in the object's angle divided by the time it takes for the object to rotate through this angle. Now as an example, let's suppose this object rotates through some angle. In this case, let's say that the angle through which the object rotates is 45 degrees. Which we can later show that this works out to be pi over 4 radians. If the time it takes for this object to rotate through this angle, this pi over 4 radians, is 2 seconds, then we can calculate the object's angular velocity. And to do that, we'd say that the angle through which this object rotates is pi over 4 radians, sometimes just written as rads, divided by the time it takes to rotate through that angle, which is 2 seconds, and that equals pi over 4 divided by 2, which works out to be 0.39 radians per second. And that's the angular velocity of this object. Now, something I'd like to point out is the angular velocity at this point and the angular velocity at this point are identical. Both of these points are rotating through the same angle in the same period of time. And that's true of any point on a rigidly rotating object. So any point on a rigidly rotating object, whether it's this point or this point or this point over here, will all have the same angular velocity because each one of those points is going to rotate through the same angle in the same period of time. Now in the last part of this video, we're going to talk about the tangential velocity of a rotating object. Now the tangential velocity of an object increases the farther you are from the axis of rotation. And that's because a point that is far from the axis of rotation has to travel through a greater distance than a point that is closer to the axis of rotation, even though these 2 points are rotating at the exact same rate. That is, each one of these points has the exact same angular velocity. They're rotating through the same angle in the same amount of time. But since this point way out here has to travel through a greater distance as this wheel is rotating than a point that is closer to the axis of rotation, this point is going to have to travel faster because it has to cover a greater distance in the same amount of time. Now in the last part of this video, we're going to figure out how to calculate the tangential velocity of a point on a rigidly rotating object. And to do that, we're going to use the arc length formula for a circular object. Now I prefer to write this as delta theta, the angle over which we're considering the length of arc, times the radius, and that's going to equal the distance, the arc length. And to give you an idea of what I'm really calculating, the arc length is this length, this distance between these 2 points, and delta theta is the angle between these 2 lines, these 2 green lines. So one way I want you to think about this is this is the distance through which a point on the wheel rotates, this is the angle through which this wheel is rotating, and this is the distance from the axis of rotation. Let's just work with delta, which is the distance a particular point on the rotating object travels, and again that's going to equal the radius, which is the point that's going to change, times the angle through which this object rotates. Now the time it takes for this point right here to rotate through this distance is going to be the same amount of time it takes to change that angle. And so we can write that as the time it takes to rotate through this angle is going to equal the time it takes for this point right here to travel through this arc, through this distance. Now one of the things I'm hoping that you see is that this relationship here, this delta s, the change in distance divided by the change in time, is really the definition of velocity. And since this object's rotating, we call this the tangential velocity. And the other thing I'm hoping that you see is this quantity right here, this change in angle divided by the time it takes to rotate through that angle, that's really the object's angular velocity. And so we can write the tangential velocity of this object as v subscript t for the tangential velocity equals the radius, the distance from the axis of rotation, times the object's angular velocity or angular speed. And this relationship will tell us how to calculate the tangential velocity at a particular point on the rotating object.
As we continue now, just remember what I said in the beginning, that tangential velocity is synonymous with linear velocity. They're the same thing.
Linear and angular velocity, let's continue. And we're going to look at this example. The second hand of a clock is 10.2 centimeters long. Now, that doesn't mean second hand as opposed to first hand. What we mean by second hand here is the hand that measures the seconds. The seconds, right? You know that on the old-fashioned clocks or the typical wall clock, you've got one hand for the hours, another hand for the minutes, and a usually red hand for the seconds. And that red hand keeps going around the clock, ticking off the seconds. All right, so the second hand of a clock is 10.2 centimeters long. Find the angular velocity of the second hand in radians per second. Find the linear velocity of the second hand's outer tip in centimeters per second. All right, so you want to find the angular velocity first, and then from that you'll be able to get the linear velocity using the formulas and the concepts that have already been explained. Pause the video, try to do this on your own, and then resume when you have an answer or if you get stuck. So here's the setup for simply finding the angular velocity. 2 pi radians per minute over 60 seconds per minute. Okay, where does this come from? I know that there are 2 pi radians in a full circle, and that has already been explained. There are 2 pi radians in a full circle. That was explained in the last video. Now, if there are 2 pi radians in a full circle, that means the second hand of a clock, which does 1 complete revolution per minute, that means that that second hand of the clock goes through 2 pi radians per minute, which is why I wrote 2 pi radians per minute in the numerator. Now we divide by 60 because, this problem is asking us for radians per second, not radians per minute. And as you know, when you're doing unit conversions, you need to divide or multiply as needed. In this case, to convert minutes to seconds, you divide by 60. And that's why we divided by 60 seconds per minute, because there are 60 seconds in a minute. And we can conveniently cancel the units, and therefore we're left with simply radians per second as our units. And we're left with the ratio of 2 pi over 60, which equals 0.10471975551. Notice that I didn't round. There's a very good reason for that. I didn't round yet because this isn't my final answer. It's simply what I'm going to use in order to find the linear velocity. And for that, I use this formula. V equals R omega. R is 10.2 centimeters. Omega is what I just found, 0.104719551 radians per second. And then when you multiply those, you end up with 1.06811415. Okay, now that's in centimeters per second, but I'm going to write that when I write my final answer because, as I've said many times before in this class, don't round until you write your final answer, because rounding early multiplies errors and inaccuracies. Final answer, omega equals 0.105 radians per second, and v, or linear velocity, equals 1.068 centimeters per second. Another example, linear and angular velocity. A Ferris wheel with a 50-foot radius rotates at 1.5 RPM. Now, those of you who like cars, you probably have heard RPMs before. RPMs is just revolutions per minute. Revving up your engine is giving it high RPMs, high revolutions per minute. So that's all RPM stands for. What is its angular velocity in radians per minute? What is the linear velocity of a point on the wheel's outer edge in feet per minute? All right, so pause the video, use your formulas and concepts that you've learned, and resume when you have an answer or if you get stuck. All right, so if we're going to find that angular velocity, this is the setup. We know that we have 1.5 RPM. That's why I wrote rev over min. It's just the same thing, revolutions per minute. So that's where 1.5 RPM comes in. And I also know that there are 2 pi radians in a full revolution of a circle. And so I have 2 pi radians per revolution. 2 pi radians per revolution. And that equals 3 pi radians per minute because, again, I can cancel units. Just as I can cancel numbers when I'm multiplying fractions, I can also cancel units. So I'm left with 3 pi radians per minute, and that's my angular velocity. Now I'm going to use that in my V equals R omega formula to find the linear velocity of the wheel's outer edge. And that is V equals 50 because that's the radius, times 3 pi because 3 pi is my omega, and I get 150 pi feet per minute. Final answers, omega equals 3 pi radians per minute, and V equals 150 pi feet per minute. Now, in your answers, you could always give decimal forms. You could multiply 3 by pi in your calculator and figure out what it is in decimal. The same with 150 pi. But the beauty of writing 3 pi and 150 pi is because those are actually exact answers. They don't involve any rounding at all. And so really the most exact way to express things in your answers is with pi. But I'll leave that up to you. I'll make that optional. Finding the area of a sector. This will be the last screen for the day. Finding the area of a sector. Now, I put this up because I want to prove to you how we get the formula for area of a sector, which is A equals 1/2 RS. All right, the sector is the piece of the pie, piece of the pie. And it could be a piece of a pizza or a piece of a apple pie or pumpkin pie, whatever pie you like. But a piece of a pie is a sector. And as you know, you probably remember this from geometry, that when you're looking at a sector, you have an arc uh, marking the edge of the sector, not a line. You have an arc. Now, why is A equal to 1/2 RS? Okay, to explain that, let's recall that a triangle, and I'm circling that portion now with the mouse arrow. Recall that the area of a triangle is 1/2 base times height, 1/2 base times height, and that'll give me the area of this isosceles triangle. All right, now the reason R is written here, is because when you're looking at these isosceles triangles as being inscribed in this circle, well, the lengths of these two sides of the isosceles triangle coincides with the radius, and that's why I wrote R here. Okay, now where do we get 1/2 RS from? Okay, to understand this, we're going to talk about a concept that you're going to become familiar with in calculus next year, the concept of a limit. I won't go into too much detail here because you'll get more into limits in calculus. But think of it this way: this circle right now has 12 little isosceles triangles inscribed in it. Well, what would happen if we suddenly doubled that to 24 little isosceles triangles? Then you'd be cutting all these isosceles triangles in half, and then you'd be redrawing it so that all the corners of the triangles would touch the circle. Well, you can increase it to 24, 48. You could increase it to 160. You could increase it to any number. Imagine 1,000 little isosceles triangles inscribed in this one circle. Well, what's going to happen? As the number of triangles increases, this length, which I am now tracing out with the mouse arrow, that length, which is B, is going to get closer and closer to this arc length, which is S. And in fact, the difference will be minuscule for very, very large numbers of isosceles triangles. That's the concept of a limit. A limit is a finite number that a variable or a function approaches as another quantity is increased to infinity. Again, don't worry about that. This is not necessary for the course to understand how we get this formula, but I know that some of you are interested in where we get formulas, and I'd be more than happy to talk about it in class if some of you would like to explore it further. All right, so as the number of triangles increases, this B that I'm now again tracing out, this B approaches the magnitude of S. So basically, as the number of triangles approaches infinity, B approaches S. Also, as the number of triangles approaches infinity, this side of the isosceles triangle, which is R, approaches the height of the triangle, and I'm now tracing that out with my mouse arrow. The height H, as the triangles get thinner and thinner, the height H gets closer and closer to the radius R. And so, as the number of triangles inscribed in the circle approaches infinity, the quantity H approaches the quantity R. And so basically, A equals 1/2 RS is derived from that because it boils down to A of a triangle equals 1/2 BH. It's just that B approaches R and H approaches S as the number of small triangles approaches infinity. All right, so that's the derivation of A equals 1/2 RS. Plug in 2 pi r for s just for fun. We know that 2 pi r is the circumference of a circle. And so, when you're dealing with a whole circle, the arc length is equivalent to the circumference. What happens if you plug in 2 pi r for s into this formula? What do you end up with? Put 2 pi r in for s and do 1/2 r times 2 pi r. And what do you get? You get pi r squared. And pi r squared is the formula for the area of a circle, as you know. By the way, just a quick joke. I remember when I was in grade school, I heard this kind of silly joke my neighbor told me. And this country boy is off to college, and actually he just came back from college. He's the first person in his entire family who's ever gone to college. And so he comes back for Christmas break after his first semester in college, and he's talking with his dad, and his dad says, "So son, tell me, what kind of stuff do you learn in college? What's it like?" And so the son says to his dad, "Well, Dad, um, we learn a lot of stuff. I'm taking a history course, an English course, and a math course." So his dad goes, "Oh, all right, what are you learning in math?" And the kid goes, "Well, we learn stuff like the Pythagorean theorem and pi r squared." And his dad cuts him off and says, "Wait, wait. Uh, I don't know if they're teaching you the right stuff. Son, everyone knows that pi are round, cake are square." That's a really silly joke, but anyway, let's continue with this. A equals 1/2 r squared theta. Why is that true? Well, we know that s, which I'm now circling with the mouse arrow, we know that s is the same as r theta. We saw that on an earlier screen. And if s is the same as r theta, then we can rewrite 1/2 rs as 1/2 r times r theta, and that's the same as 1/2 r squared theta. Now, plug in 2 pi for theta just for fun. 2 pi, as you know, is the same as 360 degrees. There are 2 pi radians in a full circle. And so if we use that for r theta, then the area of a sector will coincide with the area of the entire circle. And if I plug 2 pi in for theta, 1/2 r squared times 2 pi, I end up with pi r squared. Pi r squared, the area of a circle. Example, how big is the slice of pizza from the first example in square inches? Now recall on an earlier screen when we were doing the first example about the length of the crust in a slice of pizza. Now the question is, how big, or what's the area of the slice of pizza from that example in square inches? So use the same data that were given for that first example in order to solve this problem. Pause the video, do this on your own, and then resume when you have an answer. And sure enough, the area of that sector, or that slice of pizza, is 1/2 r squared theta. 1/2, I put 6 in for r because the diameter was 12, and so radius is 6. 1/2 times 6 squared times theta, pi over 3, which is the same as 60 degrees, but in radians. And 1/2 times 6 squared times pi over 3 equals 18.85 square inches. Classwork, page 292. Please write these numbers down, and we'll see you in class.